Teaching European project. The webinar is about an introduction to recurrent and reservoir computing neural networks. My name is Claudio Gallicchio, and I am a researcher in the University of Pisa. Okay, so like I said, this is a webinar within the aims of the H2020 European project teaching. And you can see here a link to our website where you can find more information. In a nutshell, let's say the project aims at development and deployment of autonomous, adaptive, and dependable cyber-physical systems of systems application. From a machine learning perspective and an artificial intelligence perspective, what we aim at doing is developing an artificial intelligence as a service software infrastructure for cyber-physical systems of systems that enables human-centric personalization. So how do we do these things? Three major, let's say, milestones. First of all, federated and distributed intelligence that can scale on heterogeneous devices. Second, recognition and characterization of human physiological, emotional, and cognitive state from heterogeneous sensing devices using neural networks. And third, self-adaptation and personalization using these AI models that exploit the human state in a non-obtrusive fashion. All right. Let's say after this information, so let's move to the content of the webinar. We are dealing with the aspect of learning from temporal data. So when we go to real-world applications, like we know, for example, in the teaching project, we face this, let's say, kind of structure in the information almost everywhere, okay? Like, for example, in Internet of Things application or in autonomous vehicles applications, we see, for example, that the basic idea is that we have a sensorized environment and there is a human inside this sensorized environment. The interaction between the human and the sensors determines a stream of data, let's say a set of time series data from which we want to learn, okay? And other applications, for example, are in the case of earthquakes, like I have indicated here in the right part of the slides. Not just this, but also we can do monitoring of the human beings. So, for example, EEG or ECG. So also in this case, when we record information from human beings, we have multivariate and typically also multimodal time series data, okay? We want to make sense of this data. We want to, let's say, learn, for example, to classify this ECG data based on the presence or the absence of a specific pathology or something like that. So learning from temporal data is of fundamental importance. Okay, so we want to use systems in the family, in the class of neural networks. So doing one step back, perhaps the most common and the most known kind of neural networks architecture is the convolutional neural networks. This is mostly used in the case of image processing, like, for example, image classification. The basic idea is that we, let's say, apply a distributed filter over a grid. It can be, for example, our image. We can also use pooling operators. We combine these two bricks and we achieve our neural network architecture. This is not what we are going to talk about in this seminar, okay? But just to frame the discussion, the basic idea behind this kind of neural networks is that of feed-forward neural networks, okay? So the basic idea is shared with what we call multi-layer perceptrons. And these kind of neural networks are suitable for dealing with non-time series data, so with static data, like images, for example. Okay, so and the basic, let's say, the basic way of working of this kind of neural networks is that we can see that our, let's say, neurons are organized inside a neural network architecture where we have our input information, like, for example, the image that is given in the first, let's say, in the first set of neurons, okay, encoded in the first set of neurons, or called also the input layer. Then this information is propagated feed-forwardly, let's say, from the input all the way through a number of hidden layers, and finally to an output layer when we have, for example, a final classification of our image. Okay, so behind this, let's say, neurons metaphor, okay, what we can see here is a series of nonlinear transformations of the input. Okay, so for example, the input is X. We apply, first of all, an affine transformation, then followed by a nonlinear activation function. And so what we do essentially is that every, let's say, every component in this neural network architecture, what we call the layer, okay, so those set of neurons, okay, every layer builds what we can call a neural representation of the input information, okay? And the representations in the deeper layers make the original problem that was encoded in the input layer, when it is encoded in the hidden layers, it becomes easier to be solved by a simple classifier, like, for example, a linear classifier in the output layer. Okay, so we, apart from the biological metaphor, we have, let's say, computational mean of non-linearly transform an input information X through a number of, let's say, non-linear hidden layers that compute progressively nonlinear transformation of the information. And in the end, this is used, for example, to classify the input data. Okay, so what happens when we want to, one important thing I forgot to say is that all of these nonlinear transformations are parameterized by a number of so-called weights, okay, so connection weights. All these, let's say, green lines between two consecutive layers of neurons, okay? So in practice, these parameters of this transformation are inside of these weight matrices, W's, okay? So for example, W1 for the first layer here, W2 for the second layer here, and so on and so forth, okay? So the basic idea is that what kind of nonlinear transformation it is implemented by every layer depends on this, on the values inside these weight matrices, okay? So these are the parameters that we want to, in a sense, we can tune in order to solve the problem that we want to solve. Okay, so we want to solve a difficult problem. For example, we don't know how to solve this problem algorithmically, but we have a lot of data that we have at our disposal with examples of, for example, input and output. So we want to use this data in order to tweak the numbers inside of these weight matrices. So finally, computing representations that are useful for our final classification. Okay, how do we do this? Standardly, we do this using what is called backpropagation. Okay, so we have our neural network architectures here, from the input layer in red through the hidden layers in green up to the output layer in blue. What we have, for example, at a certain point, we can compute a loss function of the output. Let's say a discrepancy between the output of our system and the expected output, what we call the target output. Once that we have this information, we can compute a gradient of the loss with respect to the weights in that specific layer. And we can backpropagate this information to the lower layers in our architecture, multiplying, okay, to the right side by increasing terms. Okay, so we can see that there is this phase of propagation of the gradient after the forward propagation of the let's say, signal information. So we have these two phases: forward propagation for the output computation, and then backwards propagation for the gradients computation. Okay, so this is the, in a nutshell, really in 2 minutes, how we do training in the case of these deep neural network architectures. All right. So one important aspect in this regard that I think is never stressed enough in the design of neural networks is that one of stability. Okay, so we want to have a stable neural network architecture, which means that the output computation should be robust to input perturbation. Okay, suppose that we don't have this property. What does it mean? It means that if I have a little perturbation in my input, this perturbation is amplified through the representations that are developed in the hidden layers, and in the end, the output can be very different. So a similar input determines a very different output, and this is, let's say, not a good property. For example, it will never allow me to generalize well with unseen data. So suppose I do successfully the training of my neural network, but then when I employ and when I, let's say, deploy my neural network in real world, then an input data comes that is slightly different from what I've seen in the training phase. So in practice, my output will be very different and not expected. Okay, so if my network is unstable, that it will tend to generalize poorly to unseen data, and this is bad, of course. But stability is also important, also when we consider the training of the neural networks. And in this case, the stability is related to that side of back propagating the gradient information. And in this case, we can have a couple of problems. One problem is the so-called vanishing gradient. Okay, so in this case, we are propagating our gradients from the output layer all the way to the first layer in our architecture. And it could be that while we are propagating through a lot of, let's say, gradient computations, the gradients become smaller and smaller. And this in practice means that there is no decisive effect of the input on the output. Okay, so when we have this problem of vanishing gradient, it means in practice that the lower layers have no influence on the output. And of course, this is bad. Another possibility that we have is that this backpropagation process is, let's say, in a sense, exploding, unstable, which means that when I backpropagate my gradients, I have an unstable process. So in practice, tiny differences in the input will determine a huge difference in the output. So this is similar to what we have seen in the previous slide. Of course, also this side of the medal is bad. So we don't want a network that is unstable under all of these perspectives. So stability in the design of neural networks architectures is one of the most important aspects that I want to stress. Okay, so this is, let's say, a general picture of the way in which we're trying to design neural networks in a proper way. Now we come to the aspect of recurrent neural networks. In the previous slides, I told you about feed-forward architectures. So we have, let's say, this input information that is propagated all the way through these hidden layers, all the way to the output layer, okay? All right, so but if I want to deal with temporal data, with time series data, then the kind of feed-forward architectures are not the ideal ones, because I have no way to remember, in a sense, let me go back here again, I have no way to remember, let's say, the previous values of my inputs inside the hidden layer. So I have no memory in practice. How to employ memory is by adding a sort of feedback connections around the hidden layers, okay? So what you see in this slide is a picture describing the basic vanilla architecture of a recurrent neural network. In this case, you have, again, three components: the red component, the input, the hidden component that is in green, and the output component, which is typically called readout in blue. Okay, the difference with respect to what we had before is that now the input is a time series. Okay, so at each time step t, suppose it is a discrete time series. Okay, so at each time step t, I give in input to my system the input at that time step. Okay, so suppose x at time step t. And now I have a representation layer, a hidden layer that is dynamical. Okay, it's no longer a simple nonlinear transformation of the input. This is, let's say, a dynamical system. that builds a representation that depends not only on the new input xt, but also on the previous inputs in a way that I'm going to show you briefly, okay? So in practice, we have a dynamical neural network that is more suitable for processing temporal forms of data, where we have these internal dynamics in the green part of the architecture that enable treating arbitrarily long sequences. So how do they perform this computation? Okay, this can be more or less complicated, but at least we need to implement a couple of equations, okay? The first equation is the state transition equation, is the equation that rules the dynamical system in the hidden layer, okay? And the second equation is a simple output layer equation that is related to the computation of the output. So in practice, what we have here, we have, let's say, a state of our system that is the hidden representation computed by the hidden layer, okay? And this is a function now of both the input at the same time step t and of the previous state, ht minus 1. Here you see the recurrency of this equation. So that's why this is a dynamical system. Once we have the state at each time step t, I can compute the output at the same time step t. I can call this y at time step t, okay? And this is a function of the state. Interestingly, these two equations are parametrized, like the case of feed-forward neural networks. So are parametrized by a number of parameters. These parameters are, let's say, collected inside these weight matrices, U for the input weights, W for the recurrent weights, and V for the output weights. Okay, so in practice, what we have added with respect to the case of feed-forward neural networks is this second term inside this first equation, okay? So now I have a dependency on the previous time step, and I can encode inside the hidden layer, let's say, all the history of the input until that specific time step. Okay, so what happens when I unfold my recurrent architecture over time? Okay, so suppose I have my input time stream, okay? So suppose I have my x1 at time step 1. This is the input information. This is fed to the hidden layer of my architecture. I compute this h1. And then through the readout layer, I can compute the output y1. Okay, so what happens next? Okay, so this, until now, this is the same thing that I could do using, let's say, a feed-forward neural network, like in the beginning of this presentation. But now we have a second time step 2, so we have a second input information x2. I propagate this information again to my hidden layer that receives in input also the state computed at the previous time step in order to compute a second hidden layers activation, okay, a second state, H2. Okay, so you can see this H2 depends on both X1 and X2 because it depends directly on X2 and depends on X1 through, let's say, this nonlinear transformation propagated through the activation in H1, okay? And then again, I compute the output Y2. I can repeat the same thing for the third time step, and I can compute a representation H3 that depends on X3, X2, and X1, and so on and so forth, okay? So this continues until the end of my time series. All right. Okay, so you can see that this kind of neural network architecture gives us more flexibility than feed-forward architectures. Okay, so when we deal with this kind of structured data, we have a lot of flexibility more, okay? So what we could do with feed-forward neural networks was this kind of vector-to-vector transformations, okay? So we have the input, we pass through the hidden layer representations to make the learning easier, and then we compute the output, okay? Like image classification. But now we can also do other things, like we can have a time series in input, and let's say we want to classify this time series. This is what I can call sequence to vector problem. Okay, like for example, sentiment analysis. I have a time series that represents a phrase, and I want to assess the polarity of the sentiment inside that phrase. Or for example, I can do sequence transduction, where both the input and the output are time series. And this is useful, for example, for human activity recognition. Or still, I can have even more flexibility. I can do something like a vector in input and a time series in output. This is what I can call vector to sequence, like image captioning, where you have an image and you want to let's say generate a description of that image. Or finally, I can even have a sequence to sequence, which is quite famous, sec to sec classification, for example, for machine translation, where I have a time series in input of a certain length, and I have a time series in output of a possibly different length. Okay, so now for our purposes, I guess we can focus to the sequence transduction and sequence to vector cases. But bring in mind that recurrent neural networks give you the flexibility of dealing with all of these possibilities. Okay, so I want to stress other features of recurrent neural networks. Regarding the forward computation, one intriguing aspect is related to the fading memory. Fading memory means that the influence of inputs far in the past vanish in the current state. And this is due to the fact that we are doing many nonlinear transformation of the input information. Okay, so we said with recurrent neural networks, now we can deal with time series of arbitrary length. This is possible, but we need to be aware of the fact that we can encounter a problem called fading memory. Okay, so for example, here in this, let's say, last representation of my time series, okay, here in this state, let's say in this green part of the network, I can say that my network has developed a representation of the entire input time series, because like we have seen, the value of the state computed at this time step depends on the input provided to the network at all the time steps. But actually, essentially here, I can see that I have many nonlinear transformations for the very old input time steps. Okay, so this fact in practice makes the state here in the green circle depending more on the last part of the time series than on the first part of the time series. And a related aspect, let's say, a related difficulty is achieved when it is observed, let's say, when we deal with training of these recurrent neural networks. So how do we train this kind of recurrent neural network? Similarly to what I showed you in the case of feed-forward neural networks. So suppose at a certain time step, I have the input, I compute my state, I compute the output, then I receive my loss, and I update the weights, okay? Then I repeat this process again and again until I reach the end of my time series. But now, what I want to do in practice is to effectively transmit this loss information backwards in time along the layers of my architecture, okay? And like I see here that there is a problem in transmitting effectively the input information through these many nonlinear transformation, there is a similar problem here when I want to, let's say, transfer this loss information across all of these layers transformation. So I can encounter in practice the same vanishing or exploding gradient problems that I show you in the case of deep neural networks, even in the feed-forward case. Okay, so in practice, this means that if I want to train a recurrent neural networks on long-term dependencies, this can be difficult. There are ways to overcome this difficulty, let's say architecturally, so introducing gates in order to, let's say, create shortcuts paths, let's say highway paths from this time step, let's say, the last time step to the previous time steps. These gating mechanisms are popularized by the long short-term memory and gated recurrent units architecture. But these kind of neural networks make the learning problem, let's say, even more complex. They introduce a huge number of, let's say, weight matrices in addition to those that I showed you before. Okay, so essentially the real problem is that when I want to train a recurrent neural network, then this is a very slow process. And either I accept the fact that I have a slow process, or I require, let's say, a kind of high-performance computing support. Okay, for example, I need to use GPUs to do an effective learning of this kind of neural network systems. So, in practice, what I want to say is that we need to find alternatives. Okay. And actually, we can find alternatives. And the alternatives that I want to introduce to you is this reservoir computing framework. Okay, so I said that when we deal with recurrent neural networks, we introduce dynamics inside the hidden layer. Okay, so what is the core idea of reservoir computing? Just focus on the dynamical system aspect of this hidden layer and forget about training the hidden layer, okay? So the recurrent hidden layer can be studied, observed, and analyzed, also instantiated like a discrete time nonlinear and non-autonomous dynamical system. So after all, what it does is just computing this kind of state transition equation. All right. So the basic idea behind reservoir computing is that I can use randomized weights instead of trained weights, okay? So the parameters that I had in this input weight matrix and this recurrent weight matrix that needed to be trained and that, let's say, determine the problem of, let's say, vanishing gradients or exploding gradients can be, let's say, completely not done, okay, if initialized in a proper way, and we are going to this aspect very soon. Okay, so the basic idea, I use randomized weights instead of trained weights. Okay, so I call this component, the green component here, I call it reservoir, because, let's say, in a sense, it should give me a rich pool of random dynamics, random oscillators, let's say, that depends on the dynamics of the input. So that I can, let's say, linearly combine between these nonlinear dynamics that I have in my reservoir layer, even linearly, in order to compute my desired output. Okay, so this component in green is called the reservoir of the architecture, and this, let's say, this paradigm has been implemented in many ways. Okay, for example, in spiking neural networks, it is called liquid state machines. In, let's say, more standard discrete time version of the equations, this is called the echo state network. Okay, all right. So the basic and cool thing of these networks is that only the output function, okay, can be trained. So this blue part of the architecture here on the left. In practice, if I avoid training this green part of my neural network system and I focus on training only the output function, of course, I have a much faster and lightweight system to be trained, okay? And you have speed up in practice in terms of orders of magnitudes for your training algorithms. Not only that, but you can also scale to edge distributed devices, because you don't need, let's say, the GPU, for example, to train all the weights in your system. You just need to train very simply, like I'm going to show you in a minute, the readout part of the architecture, and then you're done, okay? All right, so this is the state transition equation that is implemented by, let's say, a vanilla recurrent hidden layer. So we have the weights, the input weights inside this matrix U and the recurrent weights inside this matrix W. What reservoir computing is all about is about finding a way how to freeze these two weight matrices instead of doing training in these two weight matrices. Okay, so how can we do this trick? Okay, remember, one of the fundamental things in neural networks architecture is stability. When we deal with time series data, this stability aspect is even more important. Okay, so what we do in practice is we enforce a kind of stability property to our system in order to initialize it properly. And let's say be more or less sure that even in the operation phase, the system will remain stable. In literature, this property is called echo state property. So again, using a metaphor, the state, this HT of the reservoir, should be an echo of the input, okay? Should resemble the dynamics of the input, in a sense. Should represent in a high-dimensional feature space the dynamics of the input. Okay, again, other definitions of these echo state properties, let's say, are the following. The state should asymptotically depend only on the driving input signal. And dependencies on initial conditions, or equivalently on input perturbations, should fade away after a transient. In practice, this is, if you are familiar with dynamical systems, this is a global asymptotic Lyapunov stability condition that I want to enforce in my system. And how I can, what does this mean, let's say? This means that suppose I have, let's say, three possible initial conditions from my system. Okay, so an initial condition x0 and two perturbations z0 and v0. Then suppose my system is driven by the same input, time series. Then in practice, if I have stable dynamics, my system started from x0, z0, or v0 will, let's say, develop an orbit or a trajectory in the phase space that will be locked to a unique attractor. This attractor is not a fixed point, a single point, because here we have a dynamical input that is given at each time step to my system, so it's an orbit. And in practice, this orbit, in a sense, does not depend on the initial conditions. So even if I perturb slightly my initial conditions, that I am still locked after an initial transient to the same unique attractor orbit of the system. And in this case, I have the echo state property. So if I am able to initialize my reservoir neural network in a way such that this behavior occurs, then fine. The opposite, let's say the other possibility, is that I have unstable dynamics. So when this echo state property condition is violated, what does it mean? That it means that if I do a little perturbation in the input, or equivalently, like it is represented here, on the state of the system, then let's say all the possible orbits of the system, let's say, will never synchronize. Okay, so the differences in the initial conditions will be amplified over time, and let's say I will have different trajectories in the phase space. So like I showed you, like I told you at the beginning of this webinar, unstable dynamics are not good because, for example, apart from being difficult to train, but in general, they also are prone to overfitting. So you can do, you could do a good job in training, but when you are, let's say, in operational phase, when you receive new inputs to your system that you never seen in the training phase, then the orbits that you have in the system can be completely different from those that you have observed in the training phase. And so, I mean, you can be even good in fitting the data, but then you will never be able to generalize well on never seen data. So on the test part of your data set and in operational phase, the behavior will be bad, okay? And you don't want this, okay? So this is an insight on why we want to let's say, constrain our weights in order to fulfill a property like this one, a stability property like this one. So in literature, there is quite a number of works in literature, and I have pointed out here in this slide my favorite one. I think this is really a good point to the literature, a really good paper. But the basic idea in practice is that we can just focus on the weights inside this matrix W and control its eigenvalues in practice, or in general spectral properties of this recurrent weight matrix. You can find in literature a couple of conditions that, let's say, lead to the ecostate property, this stabilization property that I have described so far. One sufficient condition is related to the maximum singular value of this matrix W. If this is smaller than 1, then I know that for every input, my system will be contractive, and I, let's say, will fulfill this stability property. But this is too strict in practice to be used. So what is used in practice is this second condition, which is not sufficient, is necessary in theory, but in practice almost always is okay to be used in real-world applications. In practice, is a condition on the spectral radius, so the maximum eigenvalue in modulus of this weight matrix W. Okay, so this quantity should be smaller than 1, and we are lucky because both these two properties, the let's say the maximum singular value and the spectral radius of the matrix W here are linear operators. So we can have a very simple process to initialize the weights here. For example, we can pick random weights from a uniform distribution in -1, 1, for example. Then we normalize with respect to the spectral radius of the random matrix that we have achieved. Finally, we multiply our let's say, normalized matrix by a desired value of the spectral radius. Okay, so this spectral radius, in a sense, is the crucial hyperparameter of my system. So the initialization phase is very simple, straightforward, and after that, you don't need to train the network because you have stable dynamics that represent the input time series in your hidden layer. Okay, so another way in which, another perspective, let's say, in which we can see this thing is like if we are scaling the weight matrices. Okay, so in a conventional recurrent neural network, what you do is you train all the weights inside these two weight matrices U and W. Now, what we are saying is that actually what cares is not all the weights inside these two weight matrices, but let's say macro properties of the dynamical system, and in particular stability. So we can just, for example, fix these two weight matrices U and W, and we can tune only the scaling, the magnitudes of the weights inside these two weight matrices. I didn't say anything about the input weight matrix. This is, let's say, normalized and then rescaled by another hyperparameter that is called input scaling, often in literature. Okay, I indicated this by omega here. Okay. So in practice, we have these two hyperparameters, this omega, that in a sense determines the magnitude of the weights in the input part, and so in a sense tells us how much is the impact of the input in the new state. And then we have this other hyperparameter rho, that is the, let's say, the spectral radius, like I said, of the recurrent weight matrix, that tells us how much the state is rescaled in the phase space. So in a sense, dissipated or expanded in the phase space locally to every point in the orbit. Okay, so this is a more involving aspect. But in a sense, this is a parameter that tells us how much memory do I want to have in my system. Okay. And why does this approach work? There is a number of theoretical mathematical argumentations that we can say, that we can use to explain why this reservoir computing approach works in practice. For example, I could say, the Tekens theorem for the embedding of a dynamical system into a fixed feature space. But another, let's say, important aspect that I want to stress is this of Markovian architectural bias of recurrent neural networks. There is a quite extensive literature on this aspect too. And as you can see in the slide, without any bias, I have indicated one of my papers to refer. So if you want to have more information on this aspect, you can go there. And this is actually my first journal paper, and I am quite happy to describe what's inside of that. So in practice, why ecosystem networks, why reservoir computing neural networks work in practice? I think the most interesting motivation to this is that they exploit the architectural bias of recurrent neural systems and in general of iterated maps. What does it mean? It means that if I have a dynamical system that is contractive, this is quite, this would require quite a lot of mathematics, but in practice, it means that the system shrinks, okay, at every time step, in a sense. So if I initialize my system according to the ecostate property, I can say this, then in practice, the representation of the time series that I am developing in the hidden layer, in practice, is based on a suffix-based separation, okay? So in practice, even before training of recurrent connections, if my dynamical system is contractive, so it fulfills the ecostate property, then it is able to separate input histories based on the suffix. So to see this in the picture, for example, in the right side of these slides, I have represented four time series. Okay, the first two share a common suffix, in this case of length 2. And if we see in which state, in which point in the phase space they are mapped by the reservoir, we can see that they are mapped into very close points. Okay, and okay, so in practice, the suffix of these two time series is in common, and this fact makes, let's say, the representation in the phase space very similar. The same happens for the last two time series here. They share a same common suffix of length 2, AB. So these two time series are mapped into the phase space in the same in points that are very close to each other here. So in practice, if my problem, so the problem that I want to solve, is in agreement with this kind of suffix-based organization, then fine. My ecosystem network or reservoir computing system is able to solve this problem very easily, because here, for example, if I want to classify these two time series, for example, like positive, and these two time series like negative, then fine, I can use a linear classification here. Linear classifier will put, let's say, a separation hyperplane here and will discriminate in a good way the two cases. But if my problem, let's say, is not in agreement with this suffix-based organization, so the output of my system should not depend largely on the suffix of the input time series, then I might have a problem. Okay, like for example, here, suppose that one of these two time series should be classified with a positive way, in a positive way, and the other one should be negatively classified. And the same here, one positive, one negative, then I can have difficulties in find a proper, let's say, hyperplane that separates well these two possibilities in my phase space. Okay, so why reservoir computing works in practice? It exploits this, let's say, ability of contractive mappings to separate input histories in the phase space based on the suffix. Okay. All right. So other properties of our reservoir neural networks. We said it is, let's say, a fixed, untrained, recurrent layer. So the recurrent layer is fixed. But also, typically, in practical applications, the recurrent reservoir layer is also large. So the number of neurons you put inside the reservoir is large, typically in the order of hundreds or thousands even. Okay, so more or less 10 times more than what you would have in a neural network outside of these kind of architectures. Okay, so if you have a recurrent neural network, you can have, let's say, orders of tens of neurons. In this case, you have orders of hundreds of neurons inside your hidden layer. But so you can say, okay, now we are not doing training, but we can have a larger expense in doing the computation. This is not really true, because these connections can inside the reservoir, so the weights inside the reservoir U and W can be sparse. Can be made sparse, and so we can use, let's say, sparse matrix operations, and we can still have a lot of advantage with respect to fully trained neural networks. So the reservoir typically is fixed with a large number of neurons and sparsely connected. All right, so the last part of what we need in order to properly organize our system is related to the training of the readout. Okay, so now we have seen all that we need to know about the reservoir. We know how to initialize the reservoir. So instead of training, we focus on initialization only. Now we have instead to apply learning on the readout. So in practice, we focus on this weight matrix V here. And we want to, tune the weights inside this matrix properly, depending on the input examples that we have. Okay, so what do we do? Okay, the first thing that we do is we drive our reservoir system with the input time series. So what does it mean? We apply this equation ht equal blah, 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 a number of times. So we compute all the states, h1, h2, h3, and so on and so forth until the end of our time series. We collect all of these states, all of these activations, h1, h2, and so on, inside a matrix H, big H, this one, okay? Similarly, we can collect all the target values, so all the desired output values inside the matrix Y at, okay? And then assuming, okay, here that this is a linear function, so Fy is actually not a nonlinearity, but it's just like a linear function, we can compute the output weights in one go, directly, simply in closed form, using, for example, ridge regression, okay? So essentially, we can compute V in one single operation, okay? So here I also have, okay, if you're familiar with ridge regression, you will have noticed that this lambda here in this equation is the Tikhonov regularizer. Okay, I can tune this other hyperparameter in order to decide, let's say, how much is the sensitivity that I want to put in my system. Okay, so in practice, here I have very simple operations. I have this weight matrix. I have, sorry, this state matrix H, and I have my target matrix Y at. Okay, I combine these two matrices in one go, and I achieve the weight values that I have to put in my output layer. So I don't have epochs, for example. In this case, just in one epoch, I complete my learning, and that's very cool, and it's really fast. Another cool thing that I want to indicate you is that actually you can also exploit batches, and we are going to exploit this also for the purposes of teaching, also for the case of federation learning. Sorry, forget about these equations on the right side of the slide. So we said that we want to compute our output weights using this formula here, the formula of, let's say, ridge regression or Tikhonov regularization. Okay, and suppose at certain point I have the first batch of data. My batch of data are represented like Y at and X1, H1, sorry. So I receive my input, my batch of input, I compute this matrix H1, and I have my target information for this first batch. Okay, so I can compute these two matrices, A1, that is Y1 at times H1 transpose, and this other matrix B1. Okay, that is H1 times H1 transpose. So these two parts, this is A, this is B. Okay, so I compute for the first batch A1, B1. Then a second batch comes and I do the same operation. So I compute A2 and B2 similarly until I receive my ith batch. Let's say, for example, the last one, and this is A, and then here I can compute A1 and B, AI and BI similarly. Okay, so I can compute individually for every batch that arrives to my system these two components of this formula here, and then finally I can aggregate all of these. So I can simply sum all of these matrices and all of the B's matrices and aggregate them in order to compute this matrix V, okay, the output matrix V in this fashion. So I have this A here, this B here, that is, let's say, a way to aggregate step by step all the information that I had in this single equation. Okay, so you can consider, for example, for the purposes of teaching, if I have a number of data that is, let's say, a batch of data that is achieved on one vehicle, on another batch of data that is, let's say, generated on another vehicle, then I can finally, in my, let's say, aggregator, consider the training of the network, like if I had all the data together, just transmitting, let's say, these two matrices A and B. Okay, this is a cool property of this reservoir computing system. So reservoir computing systems is, let's say, all about linear algebra in a sense in this part, and dynamical systems. So there is a lot of space to do cool things with these aspects. And another cool thing that you can do is study the let's say, the topological properties, again, from a linear algebra perspective of the reservoir system. Okay, so the question here is, okay, I know the reservoir is cool because even if I don't apply learning to its connections, if I know that it is stable, then I can use it for doing my classification or regression tasks over sequences. But this is, let's say, typically achieved by using a random initialization. So can I do something better than doing just random? Yes, the answer is yes. And for example, one cool answer is given by the study of orthogonal dynamical systems. These systems has a number of properties. For example, they can have a longer short-term memory. Okay, so one very simple way of achieving an orthogonal dynamical system is using a permutation matrix for the recurrent weight matrix of my system. What does this mean? That I can, let's say, connect all the neurons inside the reservoir in a ring or in a cycle. Okay, so in practice, I have, again, sparsity, but now sparsity is deterministic, it's not random anymore. And so you can see in practice, I'm giving a structure to my recurrent weight matrix that is like all the subdiagonal elements are not 0, and the top right element in the recurrent weight matrix is not 0. All the other elements are 0. Okay, this is very, very simple to develop. Okay. Okay, so basic advantages of reservoir computing. Faster learning, and we have seen this a lot, so you don't need to apply learning to many parameters of your network. Okay, from the research perspective, it also allows clean mathematical analysis, okay? For example, for the architectural bias of recurrent neural networks. So what can we do with recurrent neural systems apart from the learning algorithms? Okay, so intrinsically, due to the architecture. And third, this is very cool in my opinion, it also allows unconventional hardware implementations. For example, in photonics. Okay, so in practice, what does this mean? As the dynamical part of the system does not need to be trained, does not need to be modified over time, then I can employ it using, let's say, the computations that are intrinsically performed by a physical substrate, like, for example, photonics. So I can implement all the reservoir computing operations inside a photonic system. Okay, and you can see here a couple of cool references to the literature for these kind of applications. All right, applications of this reservoir computing paradigm is, under several perspectives. Like I said, when I told you why reservoir computing works, the theory tells us that if the problem that I want to solve over time series is related to the Markovian bias, so the suffix of the input time series is the most important part to determine the output, then cool, I can use the reservoir. Okay, so in practice there are many cases in real world where this Markovian bias is met by the problem that I want to solve. For example, in ambient intelligence, when I want to perform a task like human activity recognition, so I want, for example, to identify what the user is doing based on some readings from sensors in the environment, then clearly this kind of problem meets the Markovian bias characterization, because of course the readings of the sensors on what I am doing right now are more important than the readings of the sensor, like, for example, some minutes ago. Or, for example, think about robot localization. The position X, Y, Z, or orientation also of a robot, for example, in a hospital, depends more closely to the last part of the readings from the sensor than from the first parts. Okay, and okay, just to frame, maybe to be more complete, one counterexample is given by language processing. Now, when we consider speech or sentence processing, natural language processing, and so on and so forth, for example, the first part of a phrase or a sentence could be more important than the last part of a sentence. So in that case, reservoir computing systems might not be the right choice, at least to start with. Okay. So here you can see a number of real-world applications where we have successfully used this concept of reservoir computing, like I said, human activity recognition, robot localization, early identification of earthquakes from seismographs, also medical applications like the estimation of clinical exams outcomes, but also in a currently active project called BRAID, the early identification of rare heart diseases from ECG. Of course, we will have in our teaching project many applications in relation to the human-centric interactions in cyber-physical systems of systems. I would like to, let's say, conclude with a couple of examples of applications that we had in our previous projects. This example comes from the Rubicon FP7 project. In this case, okay, the idea was to develop a robotic, intelligent robotic environment, okay, intelligent robotic ecology, let's say, where there is this human inside, let's say, a home environment, and the environment is sensorized. In this case, we had more or less, even more, I think, than 50 sensors in the environment of several nature. Okay, some of them were, let's say, pressure sensors, other were light sensors, microphones, and other kinds of sensors. Okay, magnetic sensors, etc., etc. So in practice, here we have the human that performs his daily life activities, and inside of some of these sensors, we were able to implement the ecostate network systems that not only were able to, so the sensor was not only able to record the readings, okay, so for example, the RSS information, okay, from the user, but also to, for example, locate the user inside the environment. Okay, so in the sensors, we also were able to implement these eco-state networks. And so you can see here, for example, there is, okay, a plot of what was, let's say, achieved by the system. So the red part was the target, so what the user was actually doing, and the black part was the estimated, output by the eco-state network. So you can see in practice we had very good performances. So we were able to effectively embed the intelligence inside the sensor network using this concept of eco-state networks. A final example I want to give you is this coming from the DOREMI FP7 project, where we were targeting clinical applications. Okay, one interesting thing that we did was the following. In that case, we were dealing with patients that had a number of problems. Okay, problems that can be related, for example, to pathologies or to the fact that we deal actually with elderly people. So okay, so in general with impaired people. And one of the things that were important in that case were to, let's say, assess the stability condition, so the balance ability of these people, for example, after a surgery, or let's say after a treatment or during the treatment, so that the medical staff could tune the treatment based on the developments of the user during time, okay, of this person during time. One of the clinical assessments that were required and that were performed was this balance assessment. Okay, and how to do this balance assessment typically was done in the following way. The person goes to a hospital or to, let's say, clinical facility. Then it performs a number of physical exercises, 14 exercises with 20 to 30 minutes in the clinical facility. Okay. At the end, the clinical staff evaluates all these performances, let's say, of the patient, and give a score. This score goes, for example, from 0 to 56 in this case. All right. So what we did, we developed a system based on, again, eco-state networks. We had what we call this sensorized carpet. This carpet can record the pressure value, okay, so using pressure sensors in the 4 corners of this carpet. And so we asked simply to the user to step on this carpet, perform a very simple exercise among the 14 exercises that were present in the clinical test, and get down from this sensorized carpet. So essentially 10 seconds of time required to the user. Okay, so instead of 20 to 30 minutes, 10 seconds. We collected this data. This is 4-dimensional data in this case, and we use this 4-dimensional data to train, together with the estimated value given by the clinician, to train our eco-state network model. And we were successfully able to estimate the value of the clinical outcome based on the input data coming from the pressure sensors on the sensorized carpet. Okay, so this is another example of cool applications of eco-state networks. All right, I have a final part of the slides in which I show you something about the theoretical developments in the deep learning settings, so deep eco-state networks and deep reservoir computing, but I think we are running out of time, and I can just point to the implementation in TensorFlow with Keras of eco-state networks and, let's say, deep learning development in deep eco-state networks that you can find on my GitHub. So we are starting the development in teaching. We actually started the development in teaching from this kind of from the code in my GitHub that you can find here. So you can also have fun with that, go to that, download it, try to use it instead of your recurrent neural networks layer. And okay, you can see it's quite easy. Of course, you can use this, and if you have any difficulty, just drop me a line. This is a work in progress. And this said, going to the conclusion, stability in neural networks architecture is a fundamental concept. It is possible to leave the internal connection of a neural network untrained if stability is under control. Okay. What I try to show you in this webinar is that reservoir computing and deep reservoir computing allows you to have fast and effective learning in structured domains, so in temporal forms of data, both accurately and in a fast way. All right, so this concludes the webinar, and I thank you all for your attention. I guess we can now move to the question answers part of this meeting.